So I'm Naren. I'm from Shastra, which is located at Tanjavur, Tamil Nadu. So I just want to know first interact with the participants, and it's very happy to be as part of the FOSSEE workshop as a resource person and take this session of the Eulerian model. So good morning to all, and you can just put it in the chat box. May know your like kind of affiliation, like you are an undergraduate or faculty, postgraduate student, PhD student, and which branch. I mean, the participants. You can just put it in your chat. Maybe you're a BTech student or an MTech student, faculty, and which domain. Someone has put a PhD student. You just maybe write your name, affiliation, and institute. Like for example, I'm Naren, I'm faculty from chemical engineering, and I'm from Shastra. Okay, so we have someone in MSc physics. So there's a thermal science student. Okay, so we have people from motor sport engineering. So that's nice. So MSc Advanced Motor Sport Engineering. Where is this? I think Mr. Parth. This is from which institute?
Hi, Naren. It's from Cranfield University in UK.
Oh, fine. So that's
Yeah,
nice.
yeah.
Right.
It's a specialization course mainly in
Yeah.
motorsport, and I wanted to focus on CFD and aerodynamics.
Okay. Right. So your PhD chemical engineering, thermal fluid science. I think we have turbo machines technical support engineer. So I think Mr. Raghavendra is from an industry, I suppose. So you have a Mr. Jibin is from, I think, BTech mechanical. We have polymer chemist. Okay. So this is just a kind of a warm-up session. I just want to know what is your background, so that I can tune the talk or the delivery appropriately. I mean, I can tune the talk dynamically. At least it suits. I mean, I have planned something based on what I got to see as a list uh, uh, from the registration. I just went through the list, but just like that, I want to reconfirm so that based on your background, I would know whether what I have planned for today is in something like it is in sync with what you are expecting as such. So participants, you can just put your name, you can put your affiliation, and you can tell whether you are from which background, BTech, Masters, PhD. So there are about 39 participants. How many of them are very new to CFD? I mean, is this the first time like you are getting exposure to CFD, or you already have done some CFD simulation? Or maybe you would have done some single phase simulation, but multi-phase is something new to you. Something like that. Can you chat? So I think Ms. Swapna said, I am new. Okay. Okay. So many are multi-phase is new. Okay. I could see there are completely new to CFD. Okay, fine. Right. Single phase aerodynamics, I think Mr. Parth has done, but I think I could see many responses. If we see in the chart, I think it is new to multi-phase. Fine, good. Okay, so Mr. Anshuman has done in multi-phase in COMSOL, but probably not in open form. So that's fine. So I think, I mean, of the responses that we now see in the chat, I think most of you are new to CFD itself or new to multi-phase also. So that's good. I kind of, based on my previous experience with, like, say, interactions in such workshop, it kind of, I also made the presentation something like this. So that's fine. Okay, phase change. Somebody is asking how far is different than multiphase. It's in fact it's a multiphase simulation only, because if you have a vapor condensing to a liquid or a liquid vaporizing, so eventually you have two phase then. So that's essentially a multiphase. Okay, so there's one person who has done multiphase in ANSYS. So I presume that in open form you want to now try it out. But I think most of the concepts, at least, I think you will know. Talking about freezing and melting phase change. Yeah, that's also a liquid solid two-phase simulation. Okay, so we have got some responses, at least of the
Hello?
people. Yeah, hello.
Yeah. Sir, I have a question regarding this multiphase.
Yeah.
Can be, I have a problem. So problem is like that. You have a water and it is going to be free. So it is going to be expand in volume, right?
Okay.
So how we can model this in commercial package, because in ANSYS the module solidification and melting, it is based on this assumption that volume is not going to be changed. So volume is remaining to be conserved.
Right. I have so first disclaimer I want to tell is I have per se not done liquid solid two-phase simulations. I have predominantly done only gas liquid or a gas solid simulations. However, from my little experience, all I could say is this phase change is not, I mean, especially from liquid to solid or solid to liquid, it's not direct. We need to write kind of a subroutine or an additional functions and incorporate this indirectly into the solver. It is, I'm not sure whether this volume change, which is quite possible in liquid solid phase change system, is directly available. In fact, gas solid or liquid solid itself, this simulating solid phase itself, if we talk in terms of Eulerian multiphase flow, we are assuming it to be a fluid, a kind in the model. We are not actually assuming it to be a solid per se in the model. So the solid itself is imagined as a fluid and then only model, but with some terms to correct that, to know that it is like a solid. So that's what at least I can instantly respond to your question.
So okay, so if suppose there is a problem, so in which closed shell is there, inside which a fluid is filled. So if you heat the fluid, and it will eventually turn into the gas, and due to this phase change, volume will increase. So how will
this is possible because what we do is we write, that's what I'm saying. In gas liquid, what we do is if you want to do this phase change, we write this as source term. We call this as mass source term, momentum source term, and this source term is a thermodynamic source term, because what happens in phase change is a thermodynamic phenomenon, and this needs to be written as an additional function within the solver. We need to understand CFD primarily solves only momentum equation. It does not has, it cannot capture just like that a thermodynamic process. So the thermodynamic is incorporated through a function. So we can give a source term for mass, which is like in the vapor phase, it is like an addition, I mean appearance, whereas in the liquid phase, it is like a consumption, disappearance, and then it gets linked. That is doable. I hope at least I have peripherally touched what is there in your mind. Right? Do you have any insights how to start CFD from scratch? I will be working on a stirred tank. It's a very quick response to that is please take any good reference or a standard paper and then try to reproduce it. They would have written all the boundary conditions and everything. And I'm sure that there should be some open form tutorials available in the FOSSEE itself, and you can follow that and then you can change it. This is to Ms. Swapna. Mr. Raghavendra has for steam turbine with superheated steam at inlet, but the steam is expanding over the rotor and is concerned. The outlet is mixed. Can we model this problem? Yes, we can model this. This is again the same answer which I've given to the earlier person. So how much vapor has to get condensed to liquid? This is called phase change. This phase change has to be given as a source term, both in the continuity equation and in the momentum balance equation. Only when we give this, this will be captured. Otherwise, simulation does not know that it needs to condense, because thermodynamics is not as part of CFD. So let me formally begin. Good morning to one and all here. I'm Naren from Shastra, taking this session on Eulerian multiphase flow model as part of the workshop on open form conducted by FOSSEE, IIT Bombay. And I'm much, at the beginning itself, I want to convey my gratitude to the FOSSEE team, especially the open form team, which is now at least here we have Ms. Payal, who is coordinating it, Professor Kannan, who introduced me to this FOSSEE, not only just open form, to Scilab, BWC, a lot of other things. Professor Janani, who heads this open form as a PI, and obviously I have a wonderful resource person who will take the lab session, Mr. John, and to all the audience. So I only hope, and to the good extent, I'll assure that your morning time, that too on a weekend, when I think you are on the 5th day, you might be slightly tired, but still I will make sure that your time is not wasted and you find it useful attending this session. Now I'll start with this disclaimer, right? The first one is a person who's never made a mistake has never tried anything new. So that means I'm also vulnerable to make mistakes. So please don't take everything that I tell, I show you today for granted. You need to explore. You need to take clues from what we discuss now in the meet. Go read. And if you find what I have said is contradictory, I'm very much happy if you can write to me on this email ID so that I will also learn. So learning is a two-way process, and it is not one-way process. So feel free to write back to me so that at least when next time I take a workshop, I will rectify myself, or I will also learn. And the next thing which I want to follow, usually in terms of all my lectures, is we should not make things complicated beyond what is necessary. Just because we know how to deal with complex stuff, we should not invent complexity and then resolve it. We should only keep things as minimum required for that day. So that means what? I am certainly planning the lecture at a very kind of a basic exposure level, because the idea is not to make you master of Eulerian multiphase flow in 1 hour. Now, if I can claim that all of you will become masters in 1 hour, I think that's a very tall claim, and that would be mostly a dishonest claim from me. So I'm not saying you will become, or my objective is to make you masters in 1 hour or an expert in Eulerian multiphase flow. I want you to introduce you to multiphase flows. It is like if you go to a shop and you see a lot of sweets, you just take a sample of sweet and then taste it. If you like it, you will buy it, you will taste it more, you will keep visiting it, buying it. That's it. So I have to just provide you a taste of what is Eulerian flow. And I'm assuming that in this due course, I would have made a chance to really make you understand that it is required as part of your process. This picture, if you clearly see, it shows that the person is chiseling by himself. So, which means to say that if I have to grow, I have to chisel myself. I will be the anvil, I will be the hammer, and what I will discover is also whatever is from me. So that means learning is a very, very conscious commitment of the self. That is what I truly believe. Others, including teachers, friends, peers, they can inspire us. They can show how they have built themselves. But eventually, if we want to become strong, it should be what we want here. Now, with this disclaimer, again, this is a kind of a different thing. I don't want to show the references at the end. I want to show the references at the beginning. These are some of the references which you can go through later on in case if you want to read about multiphase flows in general or about also Eulerian multiphase flows. With this pre-information, this is a quick outline of what I'm planning for the day. I'll just quickly recap what is your relevance of CFD or what you have, bits and pieces of what you have learned so far. I'll talk about what is multiphase flows, and I will again touch up what Professor Raghavendra has done yesterday in terms of different approaches for multiphase flows, and then directly go into Eulerian and tell about briefly about what is interface, and then tell what is the framework of simulating Eulerian model, and that's where we will end. So the idea is to give you a flavor of simulating multiphase flows in an Eulerian context. So during this course of 5 days, are you fine with the concept of continuum? Do you understand what is continuum? Now, this can be interactive. Otherwise, I may not be able to see the chat because at least if I have to see the chat, then I have to see it in another system, which I don't want to do now, at least. So you can feel free to unmute and also speak in between, at least one or two. So I think the concept of continuum is very clear. Yeah. So first thing, what we should name is the continuum. So that means we do not see molecules in CFD. So that means if you have a system, okay, which is filled with water, that means we see complete space is filled. We are not seeing this as molecules. So this molecular picture is something that we do not, this molecular picture is something that we do not see. Is it clear? This is something that we do not see. This is what is the concept first of continuum. So we should know that what we are seeing is actually a space that is completely filled with the matter. And typically we are talking about the phase that is filled with the fluid matter. So this can be gas or it can be liquid. So this can be gas or liquid. But eventually, even for solid, that means we are seeing only continuous thing, right? That's what the starting thing which I want to emphasize. Now, how is this continuum found out? This is by Knudsen number. So are you aware of what is this means, lambda by L? I mean, any idea of lambda by L, or you want me to tell what is lambda by L?
Yes, sir.
Okay. So I am getting a response, so that's nice. So that means how is continuum decided? It is divided by Knudsen number. Now one can write as L by lambda or lambda by L. This is like mean free path. And this is the characteristic dimension of the system, right? Now, based on if Knudsen number, which is lambda by L, suppose if it's much, much greater than 1. So that means you have a large dimension and mean free path is very less, then that means you will see it as continuous. That is what happens in the room. In the room where we are sitting, we see the room to be continuously filled with air. I mean, filled with nitrogen and oxygen. You don't see molecules because why? The mean free path is very less. It's the order of 10 power minus 6, 7, depending on like, and then the length of the room and the breadth of the room is hugely high, right? So that means before a molecule travels from one end to another end, it will collide with huge numbers. Suppose if you have a molecule here and you want this to reach to this end, if the lambda is much, much, much less than 1, then that means it is like telling there are so many molecules here. I mean, so many entities here. So that means this molecule of our interest will collide with so many other particles, and only then we'll be able to reach this. This is what it means, Knudsen number less than 1. On the other hand, if the Knudsen number, if it is given by this, right, if it is greater than 1, I mean literally greater than 1, which means you have L is very less than lambda. Is it clear? So that means it is like telling I have a system where here I have one molecule and then, I have a system where the system boundary is so very, the mean free path is very, very large. So the mean free path is very large and another particle is only here. So that means nothing else is there in between. So that means this, if it has to reach here and then collide, this is huge distance than like reaching this wall. It can reach this wall very easily, or this side it can reach the wall very easily than reaching another particle. This is what happens in the extra space in the universe. Like say between two atoms or two molecules, you have huge distance. So that means essentially we will see only molecular scale. We will not see something the continuum scale. This is the idea of continuum. And I'm sure this is, you could recollect, CFD is about transport equation. Transport of what? Transport of mass, momentum, and energy within the concept of control volume. Okay. Now, what is control volume? It is an infinitesimally small region within which you are assuming that the continuum hypothesis. This is the continuum hypothesis. So you are seeing water like this and not water like these molecules. So within which the continuum hypothesis is valid. That is what is written here as V star. So if you go below this V star, so that means then your continuum hypothesis is no longer valid. If is this maybe I'll just quickly give like an example so that this is clear. Like say suppose if you take water, okay, now you know water's density is 1000 kg per meter cube. So that means 1 meter cube of water will have 1000 kg. So that means mass is to volume ratio of water is 1:1000 or 1000:1. Now, what is it? If I take 1 liter water, what is this ratio of V:N? That is also 1:1000. If I take 100 ml water, then also it is 1:1000. Suppose if I take 1 ml water, 1:1000, right? If I keep reducing the amount of water, do you think this ratio is that preserved?
No.
Right. I mean, is that no? So somebody has. You can also put in the chat because if you are finding it, I mean, not many, all people might be comfortable also. I will occasionally see the chat as well. So as somebody has responded very nicely, so this will not get maintained. Now, why it will not get maintained? Because you are breaking continuum after some point. The moment you break the continuum, you cannot use this transport equation. I'm not saying those cannot be modeled. Those cannot be modeled in the same manner as which we are modeling I'm just give me a little time. I'm just joining through another screen also so that I can at least see the chat. Yeah, so that means if you break the continuum, so there is some point after which this ratio cannot be maintained. That's what is there in this picture. If you see here, this ratio, and this is not density picture, this is something else, but I'm not going into the detail of this G function now, which is like a force function. But after sometimes there is a repulsion going on here. This is a different picture. And then that means you will not have the macroscopic density, you will have something like a microscopic density. Only if control volume is acceptable, we can have this conservation of mass, momentum, and energy in the fashion you solve in your CFD. Now, I presume again, this is something quickly you are able to recollect. What I have written is a generic form of the equation. Instead of writing three different equations, I have written it as one transport equation. So I have written as one transport equation as dou of dou phi by dou t plus, like say, what I am writing is this equation. What you see here, right? Into dou of rho into velocity times phi. Then there is dou of this gamma is actually the diffusion coefficient times grad of phi plus there could be source term. Now, what I written as phi, that is 1 if you write mass balance or like continuity. And this phi is u if it is momentum. And this is Cp into T if it is energy balance. This can be equal to mass fraction if it is species balance. So you can, it is one easier way of representing the equation in one form. Any doubt in this equation? Are you able to relate to this equation based on what you have seen so far in the workshop? You can chat. I'm actually seeing another system also here, so I can monitor the chat also now. So participants are free to respond in the chat so that it is easier. So that I know that what I speak is also being received and then I'm receptive of what is the mood over there.
Sir, if you have time, then please elaborate it in short way, this equation.
The equation you want me to tell? Okay. Without derivation, as I said, I will try to explain this in short way. Suppose, let's say we take a pipe, very simplest system, and let's say if there is a fluid flowing through a pipe, right? We want to understand the flow in this. What I mean by this is the velocity pattern. And we want to model eventually this. So that means we don't want to measure it experimentally, we want to model. So what we do is we take a very small region in this, that is what we call as control volume. Now this control volume is not having any shape. Somebody can take like this also, anything. But it is for our flexibility is what we are taking it as a regular shape, like how you see as cuboid or square or rectangle. Because we can write geometry for a regular shape. As such, there is nothing like that. It should be taken like this. Now, that means we take a very definite geometry. And then now we are seeing how the flow happens through this part. And trying to see, suppose if this is represented in y and x coordinate, can we write equations of this? Now, what equations? We need to write mass balance on this, momentum balance on this, same, and then energy balance on this. And if there is a reaction, we have to write a species balance on this. Now, all these conservation laws, these are called conservation laws. So our equations are not like data-driven equation. They are based on some physical laws of what we have arrived based on what we have observed in nature through our experimentation or by virtue of our observation, intuitive observation. What we have seen, what it means by conservation law is whatever is going in plus whatever is getting generated will have to either come out or it has to get consumed. So that means it has to get lost or it has to get accumulated. So that means if there is this red color dot, if I'm saying that it goes in, this has to either come out, it has to remain inside, or it can disappear and become something like a blue dot and then the blue will come out. Or it can remain inside itself. This is what is like kind of very, I would say a kind of a low level perception I want to bring it on. Now, this is at every instant of time. This is at every instant of time. This should be obeyed. And for every small control volume, this should be obeyed. Because it is every instant of time, this is called rate. That is why there is a dot everywhere. Everything is per unit time. It's not like it should be obeyed only for a duration of 1 hour or a block of 2 hours. It's not like that. How much ever you divide your time axis, this should be still obeyed. Now, you take this as a starting point, and then we develop the mathematics of this. I'm not doing the rigorous derivation, but how we do this, anything can go inside by virtue of motion. That's what we called as bulk motion, or it can go inside because of diffusion, which is nothing but because of a gradient. So what I mean by gradient, like suppose if you are near a very hot surface, you still feel the heat. How you are feeling the heat? Because heat is conducted. Is it clear? Heat is conducted through the molecules of, like say, air, which hits the hot object and it also hits your skin. This conduction is a diffusion process. This is the molecular means of transport. So this is the molecular means of transport. This bulk motion, this is because physically it is moving. Physically it is moving and hitting. Physically it is moving through a space. Now, what is bulk motion? Bulk motion is then represented in terms of by virtue of then mass flow rate. So mass flow rate is eventually captures bulk motion. Diffusion is captured in terms of primarily we have three laws. One is the Newton's law of viscosity. This Newton's law of viscosity is for how shear stress is transported, which is nothing for the momentum equation. Next, you have Fourier's law of heat conduction. That is primarily for energy. And then you have Fick's law of diffusion. This Fick's law of diffusion is for species. Remember, mass for mass balance, so that means for continuity equation, there is no diffusion. Right. What I mean by no diffusion, like say, for example, now you are seeing, I'm Naren and I'm sitting here now in Tanjavur. Next to you in your place, Naren is not there. But there is a gradient, right? There is a gradient, but that does not mean I can transport from here to there by virtue of molecules and then get reassembled. If that happens, that's like a mythology, right? So if you have an object here, let's say you have a table here and you have kept some object, some mass here. And here that mass is not there. It is empty, right? That does not mean this will come here, right? It will not get transported. So there is no such diffusion. Whereas if you just see what I mean by species is, like say, suppose if you have a table, you have a mass here, but only thing, like suppose this is like a scent. But you can see the scent can go in every direction. Everywhere else, these molecules of the scent can be felt. Perfume can be felt. That means it is not the mass, it is only a component in that mass can just go. This is again applicable to us. You might recognize somebody by their smell of their sweat, right? We know that if somebody is coming, we know that this person's perfume is there or a natural body odor is there. That is because the species transfer. It's not because the mass is getting transferred. So if you do all this and then put it in the equation, you eventually get the transport equation, which is what you know in continuity is something like this. This is your continuity equation. Similarly, you have maybe a Stokes equation, which is for momentum, and you have energy balance equation. Now, instead of writing it as three equation, I have written here as a single equation with the term phi, where the phi actually represents any of these, which is there in this table. I hope with this, people are able to recollect what you have seen for the last 3-4 days.
Yes, sir.
Yeah.
Thank you, sir.
I'll proceed further. So I'm not yet gone to the multi-phase. I'm trying to give you a kind of, I'm bridging you. I'm taking you from single phase to slowly multi-phase Eulerian context so that you can understand Eulerian better rather than directly jumping. Now, first thing is just, I want to show you snapshots. These are all the images taken from different portals. I have given the citation there. And this is a very good source for learning CFD and multiphase, this website. I will share this PPT through Payal Madam, and I think it will might be available to all also. That's fine. You can get to note it. I'm just showing the pictures. Can you relate to any of those or one of those pictures? You don't need to explain. You can again just put it in the chat. Can you something visualize like this in your mind? This is like a gas solid flowing through a horizontal pipe. You can just see these pictures. This is gas liquid again, but flowing in a vertical channel. This is again in a vertical channel. I'll come back to this. This is like now a three-phase pattern. So you have three phases and there are images of how they behave shown in different colors. This is something like if you have a solid packed in a bed and you sparge, you send gas from the bottom, what you can visualize. This is similar case of solid and then gas being sparged. And this is like some CFD image of a similar thing. Now, are you able to connect to any of these images? Can you visualize any of these images? So essentially, we are talking what is multi-phase. So multi-phase means more than one phase flowing eventually or present together. It should be more than one phase. What do you mean by one phase? So that means this is like a thermodynamic phase, but it's not just a thermodynamic phase. It's rather we call here as hydrodynamic phase. It is liquid, gas, or solid. So that means types of multi-phase flow we can classify based on liquid-liquid, gas-liquid, liquid-solid, gas-solid. Then we can have three-phase, which is gas, liquid, solid. You can have four-phase, which is gas, liquid, liquid, solid. When I write here liquid, liquid, thermodynamically both are liquid phase, but they are immiscible. They don't mix with one another. Now, as part of any process, right? Can you imagine that there are like multi-phase flows? Do you think that there are multi-phase flows? Yes. For example, if you most common vehicle exhaust, right? You have a gas, which is the combustion product from our engine. It flows through a catalyst bed or a catalyst converter, so that we don't send any unwanted gases, right? Or undesirable gases, pollutants outside. We have converters now, right? This is a two-phase because catalyst converter is solid. This is gas. Where if you think of a boiler, you have water which eventually vaporizes and then exchanges heat, goes to turbine and so on and so forth. So this is again a liquid, gas liquid system. Lot of our products, a very simple product, paraffin wax. Okay, I'm not talking about the non-food product, but I hope you know that was a product called Vanaspati, right? Which is nothing but hydrogenated vegetable oil, right? And this Vanaspati is solid, whereas vegetable oil is oil is eventually liquid. And how this is hydrogenated? We have to take kind of oil, right? and send in hydrogen, and you have a solid catalyst. And when you do this, this is what will get hydrogenated. All the double bonds, I'm not going into the chemistry, but just telling, all the double bonds gets hydrogenated. Like this, we have n number of cases where there are more than one phase in contact with one another. Now, if you want to design or improve the performance, what do you mean by design or improve the performance? If you want to design the volume, okay, volume of such reactors or contactors, or if you are interested in the energy rate, how much energy is consumed, how much energy is required, or what is called power consumption. Okay, power consumption. Or you are talking about force, like if it is aerodynamic, they'll talk about lift force, for example, whether lift is sufficient in that context. These are all like engineering parameters which needs to be designed, and like our work involves on enhancing this. Now, if this needs to be enhanced, these engineering parameters, they are function of hydrodynamics. Now, when I say hydrodynamics, that does not mean it is water. That is how conventionally in physics it is named, which is otherwise I would mean these are functions of fluid flow. So that means if you understand the fluid flow, you can get these engineering parameters. What do you mean by understanding this fluid flow? That means understanding flow pattern. Understanding flow pattern means how they coexist. How they coexist, what is their velocity distribution, and eventually what is their pressure drop. This is what we mean when we say this as flow pattern. So if we can capture this, then we can better design or get our engineering parameters. And if we get these engineering parameters, we can either improve the performance or like kind of design. So till this point, is that clear? Any doubt? Are you all with the flow? I'm assuming that you are all with the flow. Okay. Okay, no sir, go ahead. I got confused. So that means you are all with the flow means no sir. Okay, somebody has said yes, that's fine. So I'm assuming you are able to understand what we are trying to do with the multiphase flow. So what is represented here in picture is, even for a very simple case as an flow through pipe, right? If a gas and liquid is co-flowing, they don't have the same picture. You can see in this picture one, that means it is like more of, yeah, if you see in this picture one, it is more of dispersed, right? Whereas if you see here, which is in the picture 5, one phase is going only through the bottom, whereas another phase is going only through the top. This is something called stratified flow. It is like segregated flow. Whereas this is like one phase is completely sheared, completely mixed in another phase. Now, this you will see even in case of vertical dimensions, when the flow is happening against the gravity or in the direction of gravity. Also, we have this, we have something like dispersed. This is like something annular flow. The lighter one is one phase which goes through the center, and we have another phase which goes only across the walls. So that is like only through the walls we are sending it. Each of these flow patterns will affect, their performance will be different. What you get in dispersed flows, you will not get in annular flow, vice versa. If you want an annular flow in a system and you end up designing a dispersed flow, that means your system is not going to work. And what decides this? Before what decides this, what people did is experimentally, they actually tried to see when this picture happens. Now, what I'm plotted here is actually the mass flux. of the gas phase and the liquid phase. So that means based on the flow rates, of the two phases, these keeps changes. So that means if the flow rate is one, you have a one kind of flow pattern, and if the flow rate is different, it's a different flow pattern. This is reported experimentally by a whole number of researchers, and these are called as regime map. We are not going to discuss. All I just want to show you is there are regime maps for different kinds of phases based on whether they are horizontal, vertical, co-current, downflow, upflow, all these things. These regime maps are approximations only because they themselves are coming from experiments. So based on experimental observations, these are being arrived at. Now, this is what you see now on the screen is for a vertical flow, and then it clearly shows that you can have a bubbly flow only if it in this region. If you either increase the flow rate or if you increase this side, you will go into a different set of regime. Now, I will show one another picture and then go to Eulerian. This is something like one of my colleagues did when we were doing PhD. This is not my work. This is from a person called Dev. Dev Gupta. He is part of now Thermax now. His job was to design a corner fire pulverized coal boiler. Now, I'm not going to explain fully the process, but what I'm going to tell is what they have done as part of his PhD work. They took a boiler, okay, divided this into different zones. What you see this as 1, 2, 3, 4, 5, 6, 7, 8 till 31. And for each of these zones, they wrote a code, mass balance for conservation of mass, momentum, and species. But how are these divided? I mean, how do you know that what is the volume of each of these boxes? Because these are all conceptual boxes. These are not physical boxes, because in a boiler, there is nothing like divided over there. How are they divided? That is coming from simulations. So he did simulations. This is corner fired. You can see like this is the corner, right? Where the coal and the air is being fired. It is co-fired. There are a string of burners. You are seeing a cross section from the section view from the top. The burners are all like this. What you see here is a list of burners. And as they go to the center, they get burned and you have a kind of a fireball. This is like a kind of fireball, and this fireball raises up and eventually exchanges heat with the secondary heat exchangers, primary, secondary heat exchangers, and that is how it happens. They studied this based on the temperature profile that they get. They eventually divided this into zones and then model. So this is what CFD can do. Now you can ask why this was done. I'm not going into the detail, but at least I'll tell one objective. What they want to do is how they should tilt this zone, this burner angle. Should burner be always like this inclined at 10 degree, or should they make it at 20 degree, or they turn the burner down? Now, when the load has to be increased, when there is a demand for electricity, what they do in coal-fired boiler is they actually shift the burner up, vertically up, so that more heat goes to the heat exchangers and eventually more turbine can be run. I mean, energy can be got from the turbine. When there is no load, and when you don't want to generate so much heat, what they do is they turn down the boiler, the burner. You cannot stop a burner. What is easily can be done is to change the angle of the burner slightly down, so that means this fireball, which will, like say, suppose if it is here, the fireball moves down. The fireball, what I mean is the region, what you see here, where there is a maximum temperature. If this goes down, that means in the crossover, second pass, all this heat exchanger will get less heat, and that means less energy. Eventually, less electricity will be generated. The idea was how to know when to tilt up and tilt down. Can this be modeled? To model this, you need to model this entire combustion, and this is a gas solid two-phase system. If you model this, only then that can be done. And how this can be modeled? You can't run a CFD model in industry because CFD model does not get solved in just 10 minutes or something. You have to run probably for weeks. What can be done is only a phenomenological model. But this phenomenological model development was done through the CFD. So CFD was done mixed with this phenomenological model, and this phenomenological model is what industry can code. I mean, this is what like something that you can relate to the hardware, and based on that, you can actually operate it. So that means all this I'm speaking just to emphasize that there are multi-phase flows. Multi-phase flows occurs in different flow patterns, and there is a real need for understanding how this flow is happening. Now here comes then we move to some key terminologies in multi-phase flow, which is like dispersed phase and continuous phase. So do you know what is this dispersed phase and continuous phase? Dispersed phase and continuous phase. Continuous phase is usually the primary phase. This is like a secondary phase. Suppose if you have a system, of say liquid with gas as dispersed. So that means gas is discrete in nature. It is only in certain pockets. Otherwise, primarily, this is filled with liquid. So in this case, liquid becomes the continuous phase and the gas becomes the discontinuous phase. That is the definition of phase. The next one that you should know is something called phase fraction or phase hold-up. What is phase hold-up? It is written by a letter epsilon I for that phase I. It is a volume occupied by that phase divided by the total volume. So suppose if you have again a system with say liquid is there, and then say if you have another dispersed phase, hold up of this dispersed phase, like suppose if this is gas, hold up of gas is volume occupied by the gas to the total volume. Whereas hold up of liquid, suppose if this is liquid, is the volume occupied by liquid to the total volume. Obviously, by virtue of the definition, if you add both, so volume, that means it should come to 1 because you only have either gas or liquid in the system. Is this clear? Any doubt at this stage? The next term that we want to see is kind of phase coupling. Now, what I mean by phase coupling is, suppose if you have again a system, right, where there is liquid, it need not be liquid. Let's say this is like phase 1. Why we should always tell it as liquid? This is like a phase 2. This is like a phase 2. The questions that we have is, one will interact 2, 1 will also interact 2, 2 will also interact 1. Okay. Or is it like 1 will interact 1 also, 2 will interact with 2 also, and then 1 will interact with 2 also, and 2 also will interact 1. I mean, in which combinations is this is going to get affected, right? This is what we call it as phase coupling. Now, as I said in the beginning itself, I am keeping all the contents very, very simple consciously because I don't want to, I will take another 15 minutes. So I hope it is fine for Mr. John. John, I hope that should be manageable, right?
Yes, sir.
Right. So the idea is, it should not happen as a teaching philosophy, which I practice, that I have taught 10 pages and the participants or the students or the audience do not know what I have taught for 10 pages. I'm fine if I have only spoken 1 page, but if that 1 page is clear to the other end learners, I'm happy. So it is not how much quantum is covered. It is the quality of the information that we have understood really makes the matter. That is how is the philosophy in which I have grown up, fortunately or unfortunately. So that means I am keeping it very simple. So we can model all this. So that means we can have interactions between primary and secondary phase, primary and primary phase. Secondary phase will interact with this. Secondary phase will only affect secondary phase, something like this. How is this dictated? How is this decided? Suppose if we ask how to know this, this is usually decided by the knowledge of the phase fraction. There are some experimental guidelines or based on observation. If you have a very, very dilute flow, if this is, like say, if the gas fraction, if the gas is dispersed in liquid and if the gas fraction is very, very less than 0.01, then we usually say that liquid phase is not getting affected. It is only gas is getting affected by liquid. So gas is getting affected by liquid. That's all. Nothing else is there. This is like a one-way interaction. Right. I mean, I should actually put it's 1%. So it's 0.001. Suppose if the voidage fraction is close to like say 0.01, then maybe we will say no, liquid will also affect gas and probably gas and gas will also get impacted. This is like you are talking about, there are two kinds of such interactions. If this hold up increases, like say, suppose if this becomes more than like say 10%, then we'll say that gas also will affect liquid, liquid also will affect gas, and obviously there is a gas-gas interaction also. So this is based on experience, or I would say as observation. So that means just because when you do multiphase flow, computer will not take these interactions. We need to tell the computer what you need to do and what it need not do, what it should not do. So some knowledge of experimentation, some knowledge of visualization is required. And there are three approaches. I think this he has covered yesterday in broad. So there is a WAF approach, and other than WAF approach, there is something called Eulerian-Lagrangian, and there is something called Eulerian-Eulerian. Here, interface is tracked. Here, every single dispersed phase is tracked. Here, only the region is tracked. I won't say tracked, I would say here model. Now, what I mean by this, if you remember your yesterday's talk, suppose if you have here a liquid and you inject here, like say through a fine tip, one single bubble, and you want to see the size, shape of the bubble. So ideally the shape. If you want to shape, you need to see the interface. So that means you need to see the surface that demarcates gas from liquid. If this is the objective, I want to know how the shape is changing, then we do WAF. Now the same example I'm taking, you again, let's say that you are injecting now bubble, right? And you are injecting the bubble, like say, it does not mean that it has to be injected only once. In the earlier example also, it need not be a single bubble. It can be like multiple bubbles also, right? So just because we have drawn one, that does not mean it's single bubble. It can be a single bubble, it can be like continuous thing. Like say it can be like multiple bubbles like this also, right? You are not interested in shape. You are now interested in the motion. So that means path of this bubble. So that means you do not want now to know whether this, like say, bubble which is spherical becomes ellipsoidal as it moves up. You are not interested in this shape change. You want to know whether the bubble will go like this or the bubble will go like this. It is only the motion of the bubble you are interested. This we do by something called EL approach. Right, this is what he had, Professor Raghavendra has also told as TPM, discrete phase model. So in this case, the primary phase is modeled in Eulerian. The primary phase is modeled in Eulerian. The secondary phase or the dispersed phase is modeled in the Lagrangian approach. So that means you track every single bubble or every single particle. What I'm talking in terms of bubble is also applicable in terms of particle. Now, take the same example now again. So you have again liquid, and then like say you are injecting a bubble. Now this again can be a single bubble or it can be stream of bubbles or whatever. There can be multiple injections also. It's not like always you need to inject in single, right? You can have multiple. Now you are not interested now. You don't want their shape, right? You are not interested in motion of every bubble. What you are interested in the average motion. This is of a bubble, of every bubble. Rather, I should say of every bubble. But here you are interested in the average. Overall, where is the bubble moving? Suppose it is like telling that I want to know on an average the bubble goes like this or it goes like this. I am only interested in the average behavior. I am not interested neither in shape nor in the path of a single bubble. Then we do Eulerian, right? Typically, whenever hold up of the dispersed phase, D stands for dispersed phase. D means dispersed phase. When the hold up of dispersed phase is like more than 1%, the other two techniques are computationally very, very intensive that we cannot do. Is it clear? Now, as I shown in this case, the industrial boilers and everything else, when we have so many parameters, so many discrete phase present, in terms of their presence, volume, then that means it is really not possible, viable to do by Eulerian, Lagrangian or by Wolff method. You can only resort to do their average motion. This is like, for example, like telling, suppose if you take sand, grain, I'm talking like mud in your hand, and then you are putting it down, and I'm asking you, you need to track the motion of every single sand particle in that mud when you put it down. I think we will literally go mad. Is it clear? If I take one sand particle and put it down, that's probably you can tell how it is flowing down. Maybe if I take 10 particles and put it down, you can still see it. But if I take a handful of particles, like say marbles or sand or something like that, and I'm just putting it down and you are asking me, tell me now where everything has gone. It's like literally go computationally intensive, not possible. But what we can tell is where and all sand is getting dispersed. So we can see the region, but we cannot track now the motion of every particle. This is the differentiating aspect in Eulerian flow. So is that clear what we mean by modeling WOF to EL to EE? So EE tells the average behavior. So that means flow behavior of the dispersed phase. as it moves through the continuous phase. Continuous phase itself can be static. So that means it can be without motion, or that itself can also have a motion. So that means I would not use the word rather static, because then dynamic will make a wrong sense here. So this can be batch, or this itself can be continuous. Is this clear at this point? What is the focus of Eulerian flow? Okay. I'm assuming fairly everybody is with me and able to understand. Then let's come to the mathematical model. The mathematical model, at least visually, is very, very visually. That means when you look into the equation, it is very, very simple. What is for single phase? For example, the equation I wrote single phase equation as like this, right? Plus this is the accumulation term. Next, you have the bulk flow term. The bulk flow term is written like this. Plus, then you have the diffusion term. The diffusion term is written like this. Plus any other source term. So source term is for consumption or for production. This is for single phase. Eulerian eventually tells that there are two phases. That means it is like phase 1 and phase 2. Is it clear? Or that is what we write as continuous phase and dispersed phase. So that means the same equation has to be written twice. No change in this. This is exactly the same equation. Okay. Only thing is now this has to be written 2 times. One you have to write for the continuous phase. So I'll put everything here, C, C, C. Right, everything is C. And another, if I will put for D, which is for the dispersed phase. So visually, when you see, there is no change. But is this correct at this stage? It's not yet complete at this stage, because you have 2 equations. That's fine. One for continuous and one for dispersed. But are they connected? What I mean by are they connected is, we said in a cell. So that means when you divide this into grids and everything else, we are saying in every cell C and D can be there, because C and D can coexist. That is what you are saying. It can coexist. But are the equation now connected by what you see on the screen? Have I connected those equations, or I have only written them? It's like 2 equations discretely written. It is like 2 equations discretely written. They don't talk now. Is it clear? This talking is not established. How we establish by talking? It is through a term. One way is to account for their presence, and that is done in terms of adding now a phase fraction as part of this. Sorry. Adding not only this term, but it is like adding a phase fraction. So that means it is rho C, epsilon C, and then UC. So everywhere else, epsilon to be added. Now epsilon is added here. In this explanation, epsilon will come. So essentially, epsilon is added. So that means you don't write like rho into phi, which is like for single phase, whereas for Eulerian, I write rho of phase, epsilon of phase, and this phi of this phase. This phi of his phase, as I said, it is 1 if it is mass balance. If it is continuity, if it is momentum balance, it is velocity. And if it is energy balance, it is specific heat of continuous phase and the temperature of the continuous phase. So that means essentially we are coupling through the phase fraction. The other term which connects these two equations is this source terms. Right. Now, what is the source term in Navier-Stokes? If you remember your single phase Navier-Stokes, I am not writing now completely. So you have this momentum balance, then you have this bulk flow term, then you have this shear stress term, plus you will have pressure gradient and then like say body force term. These are all like source term. These are all called source term for momentum equation. Like this in Eulerian-Eulerian, what are source term in the momentum balance? The source term in momentum balance are called momentum exchange terms. This momentum exchange terms exchanges momentum between continuous and dispersed frames. They are equal and opposite. So that means if momentum is lost by the continuous phase, then that means it is gained by the dispersed phase. Now, each of these source terms are usually modeled with respect to a coefficient and as a function of slip velocity. So that means there is a momentum exchange coefficient. This is like momentum exchange coefficient, and slip velocity is the difference in velocity between the continuous and the dispersed phase. The question comes, what are these? Is there any names for this? Yes, and most of you would have already known this. For example, drag force is one such momentum exchange force. Lift force is another momentum exchange force. We have many such forces, like say something like virtual mass. We have something called Brownian force. Okay. Brownian force. We have something called Bassett history force. All of these. Now, if you look into all, like say the drag force, which most of you might have been at least familiar, this drag force is equal to a drag coefficient times the mean kinetic energy, and that is usually based on the continuous phase, and the kinetic energy is based on the slip, right? It is on the slip velocity. Is it clear? And the projected area of the dispersed phase. So this is the projected area of the dispersed phase. And that means this is based on the size of the dispersed phase. Size of the dispersed phase. And this is where the size of the bubble or the particle comes in. This drag coefficient, there are experiments which were already done and modeled. This drag coefficient is given as a function of Reynolds number of the dispersed phase. Reynolds number of the dispersed phase. What do you mean by Reynolds number of dispersed phase? It is the diameter of the dispersed phase times the density. Density is usually taken as a continuous phase, and a slip velocity and viscosity of the continuous phase. So the linear dimension is actually the diameter or characteristic dimension of the dispersed phase. Now we need to enable this, at least we need to enable one, and primarily drag will be always there. Drag is because of the virtue of the pressure, the normal stress difference between the two phases that is happening. So that means if you have a system and if you have your liquid, and let's say if you have now a bubble rising, this side and this side is having a difference in delta P. Usually here it will be higher, here it will be lower. So that means there is a drive. Something is pushing the bubble up. It is not only buoyant force and gravity force. There is another force which it puts. I'm not going into the explanation of drag, but I would just help you to reconnect to the famous thought experiment. I'm not sure whether it is a real experiment that Galileo has put balls of different material from the leaning tower of Pisa and then absorbed. But I would sometime later put it in the chat. I think this was done now recently. I mean, in the last decade, in the vacuum chamber in I think NASA, where they showed that if you put a feather and a ball, they will reach the ground at the same time if drag is not there. It is only because drag is there that the feather will not reach the ground and the ball will probably reach the ground faster, right? So that is shown. So eventually that is the drag force, and this drag force is one source term. So with this, for just sake of brevity of time, and I just want to give some practice, I would just give what is the broad steps in simulating Eulerian multiphase flow. First is you have to define the geometry. I think by now you know how to draw the geometry or import the mesh and define it. Next is you need to enable multiphase flow. So primarily you need to tell that you are following EE model or the Eulerian model, of which there will be one primary phase and one, this is like for the dispersed phase of the secondary phase. It is not alone sufficient that usually you will tell about gravity is acting or not, whether you want to include gravity or not, whether you want to include energy balance or not. Temperature, if you enable, it is energy balance, otherwise not. Then you will tell about the viscosity model. So whether it is laminar or turbulent. I'm not going into the turbulence of multiphase flows again for the brevity of time, but this is not enough. You need to enable now what are all the source terms. So that means or the momentum exchange. This momentum exchange coefficient. So that means we need to tell what is this beta. One of this beta is this drag force. But you can do this for lift force, virtual mass. For every such force, there is one coefficient. This we need to enable. If you don't enable, the system will not understand that it is a multiphase flow. And the next step after defining the model is the boundary condition. Boundary condition, there's no major change. If it is inlet, you either give velocity or pressure or mass flow rate. You can give it both for the continuous phase and the dispersed phase. Outlet is either pressure is specified, okay, or we call it as an outflow. So that means we say that the outlet is at 1 atmosphere, something like that. Walls are given as typically no slip if there is a fluid system. Only if it is in a solid system, there are some other treatment. I'm not telling that now. So both for the continuous phase and the dispersed phase, we need to tell us no slip. And then you need to iterate. So that means what I mean by iterate, it can be steady state simulation, or if you're going for time domain, so that means you tell the time step and the iteration. And then you look for the convergence and then do. So the only difference comes here is you need to include this momentum exchange factor. I forgot to add, when you enable this multiphase flow, we need to tell what is the size of the dispersed phase. Because you remember in my talk, I said this dispersed phase size governs this drag coefficient. What Mr. John has planned is you will do typically two simulation. One is the same simulation like yesterday, is a gas liquid simulation where there will be a region which will be initially filled with liquid, and you just patch a region. Remember, in Eulerian, it is not bubble, it is a region patched. So that means it is not one bubble. It is like that space is completely filled with gas or air. The next simulation that he will show or you can practice is a gas solid, where in terms you will fill this, now it is with particles, and then you will sparge air from the bottom. So if you sparge air from the bottom, and then that is what is a fluidized bed, and you see what happens here. Anything else, Mr. John, should I cover now? I think this is fine, I suppose.
Yes, sir.
Yeah.
So you will be available if they have
I'm
any questions.
available. Yeah. Till
Yeah,
12:15 or something, at least I will be available.
Okay.
Participants, I do understand that you might have a lot of queries, but I just want to know, at least have you got a fair idea of what is Eulerian is doing?
Yes, sir. I got the idea.
Right. And there might be a lot of questions, but that's fine. Right. I mean, the idea is just to experience what is Eulerian, how to see Eulerian different from a WAF simulation. Remember, we are giving the size, but that does not mean we are giving a bubble. We are saying that that region has gas. That's all. Right. We are not saying that region has only one bubble. It can be like 1,000 bubbles also. We are not seeing an entity. We are seeing only an average region. It is like asking where and all there is bubble. That's it. If there are, I will try to answer the questions. I think in short of time, we will not take the questions separately, but you can put your questions in the chat and I will respond in the chat itself. And I would request Mr. John to take it up from here. But thanks to Payal Madam, thanks to Professor Janani, thanks to John and all the participants for making it lively. And I only assume that there is something you have got for spending this 1 hour traveling with me this morning. Mr. John, you can take it up. Participants, you can put your questions in the chat. I will be reading the chat and I will explain there.
Yes, sir. Thank you so much. It was such an interactive and interesting session. So Professor Naren is our esteemed executive faculty partner of the Open Forum team FOSSEE, and he has been a friend of FOSSEE since long time. So thanks a lot to you, Professor Naren, for joining this session and conducting this.
Thank you, madam. It's
Thank
always a pleasure to be with FOSSEE.
Same here, sir. Same here.